I will talk about, it's really nice for me to speak today in the BUC because I will talk about something that was developed in the BUC XIV, I guess. So it was 2 years ago, and maybe I can use it as an introduction. So it was a different conference because we had 2 days of open problem sessions, and then 3 days of working on the open problems. So the story is that Hiram Blancas Benitez gave a talk on simple nested coalescence. And it was something that she developed in her PhD with Victor Ribeiro and Amaury Lambert. Put all the names. And it was, if I have some time at the end of the hour, I will talk about the simple nested coalescence. This will permit me to give some open problems if you want some more exercises. And so at the end of her talk, she asked about what we could say about the nested Kingman coalescent. I was in the room. Well, actually, I was already working with Hiram, and luckily for us, there was also Tim Rogers. Is there a D? Yes. No. Sorry. And Jason Schweinsberg in the room. So we worked together 4 days. We developed a lot of techniques to solve our problem. It took us like more than 1 year to find the good one, well, the one that we could solve for our problem. So let me explain the problem. Okay, so imagine you have a phylogeny. You want to model your phylogeny. So what is a phylogeny? It's the tree of the species, of the tree of life, but species-wise. So you have some species that eventually merge to an ancestral species. Okay, and this way you try to okay, so this is species A, species B, species C, and you know that it's good work to do to try to find the tree of life of the species and try to model the best one when we don't have any data or any good data. So the way we will model this species tree is just with a Kingman coalescent. So I will call, so here is the present times 0. And then I will go backwards in time, okay? So S of t is the number of species at time t in the past. And we will suppose that this is the number of blocks of a Kingman coalescent. So what is a Kingman coalescent? Just in one sentence, I will say that each pair of species, in this case, will merge at rate, let's say C, on all these pairs, couples of species, they merge independently from each other. Okay? So you put a clock of rate C over every pair of species, and you wait that this clocks ring, and then you merge the two species. Okay? So this is a binary merging. And so if you look at the dynamics of S of t, it is easy to see that so you will lose one species at a rate which is well, the total number of c times the total number of pairs that you have. So this is the rate, c times S of t choose 2. Okay? So the dynamics can be written this way. If we want to have a good intuition of how S of t is going, and in particular to approximate it in small times, well, we can use these rates, and so we have ds of t over dt. Well, is essentially so going down by 1 at rate which is more or less S of t square over 2. Okay, and this is, okay, so if I replace this by equal, it's really easy to solve, and we get that S of t is 2 over c times t, and if I add also, then S of 0 is equal to small s, so this is what we get, okay? Maybe I will put an approximation. So this is true when t is small, okay? Great. This is a formula that I will use a lot of times. Okay, so in the Kingman's coalescent case, it's really easy to solve, really easy to have the intuition. And then in more complicated coalescence case, you have also a result like this. So this is an asymptotic. This is an almost sure asymptotic that you can get. This is Beresticki and Schweinsberg, Beresticki and Limich, maybe more work. But I will stay in Kingman's case. Is it okay till now?
This is like the average number, or should we think of this? Or
Exactly. You approximate S of t by its expectation, and you can solve it this way. And this is true that you can approximate it by expectation. But the real result is that you have an almost sure, or in probability you can prove it quite easily, or an almost sure convergence of this divided by this to 1. Okay? It could be very informal now that I think about it. I won't put much details. Okay. Great. But now that we have the phylogeny, we want to add, so these are species, humans, monkeys, rabbits, whatever you want. So we can have people inside this species. If you want to make to model it, or if you have some data, you could have many representatives of the species. So here we would like to add guys in this species, and we would also like to look at the genealogies of those guys. Okay, so we want to make inside this species tree a gene tree. Okay, I will use species tree and gene tree, but essentially it's the same. These are coalescents. Okay, so we want to model everybody at the same time. Okay, so maybe I have my lineages going backwards in time, and they can merge, etc. Okay. So for this, I need more notations. I will call n of t, which will be the sum from 1 to till s of t, ni of t. This will be the number of lineages, the total number of lineages, or genes, I will call them, at time t. Of course, Ni of t will be the number of genes inside species I, okay? Whatever, it does not matter the way I will label my species because everything will be exchangeable, okay? So species 1, 2, 3, and you sum at any time over the number of genes that you can see in every species, okay? Great. So, and we will say that the genes, they coalesce, well, inside their species according to a Kingman coalescent. Okay? On a real Kingman coalescent with C equals to 1. Okay? So C will be the rate for the species and 1 will be the rate for the genes. Okay? So I can use the same type of approximation to get an intuition of what's going on, because now what I will try to see is an approximation for n of t in small times also. So let's say that n of 0 equals n. And we will suppose first that n is far bigger than s. So if n is far bigger than s, is it n or ni? No, ni, sorry, of 0. So what's going on? I have s species, small, some relatively, and inside I have a lot of genes. So these genes will coalesce between themselves, okay? So this thing implies that the first events are gene coalescence, gene mergers. Okay? But actually, as we have some Kingman dynamics, so we can think, I use the same formula, so ni of t in small times is more or less 2 over t plus 2 over n, okay? And this I will approximate it by 2 over t if I suppose that t is far bigger than 1 over n, okay? Right. So the picture that we have when we start with a lot of genes inside less species is that inside every species we have Kingman dynamics, blocks decreasing this way, and the species do not move. They don't have time to coalesce yet, okay? So at the end, I can make an approximation that n of t will be the sum of these guys. So n of t will be more or less 2s over t, okay? So actually, if you make some simulations, so I will do a live simulation. So if you make t, and let's say you represent log of n of t, you have, in small times, you have something going like minus t, okay? Okay. But then, so at the beginning, I have a lot of coalescences of genes, but then I lose genes, I lose a lot of genes, and then I have few genes, or at least as few as the number of species. So after a certain time, I will have some mixed coalescence, or not mixed, but I will have some gene coalescence and some species coalescence which are arriving at the same moments, okay? So this time is when t is of the order of 1 over s, or if it starts to be bigger than 1 over s, actually, on both. So you have coalescences of genes and species. And now the mess starts. Why? Because if you have a species coalescence, what does it imply? So you have your genes, which are number of genes which are decreasing here and here, but then if you look at ni of t or n1 of t, then suddenly you had genes decreasing normally, and then somehow you ny of t will double its size, so that we cannot approximate it by its expectation, if I would like to give an. So there is no way to use this approximation is just false. Okay, so I cannot say that it's more or less 2 over t, but I can try to approximate ni of t by w over t, where w is a random variable. And if this is true, I can use the law of large numbers to say that, law of large number argument, to say that n of t, which is the sum of ni of t, will be approximately s of t times the expectation of w over t. Okay? And s of t, it's okay. It's the number of species. It goes like the number of blocks in a Kingman coalescent. So this gives 2 expectation of w over ct square. Okay? And this is mainly the result that we managed to prove. And this is interesting because we have a change of shape of the decreasing. So after a certain time, which is more or less 1 over s, decrease in a bigger way. So it's not good at all, my picture, but well, you understood, no? Okay? And this is what we could find the first week with the simulations, okay? So of course, if you start with less genes, you have it from the beginning, okay? So this could be actually a way. If we manage to prove this thing, this is great because we can make how do you call it? We can make a statistical proof of is the genealogy a Kingman coalescent or a nested Kingman coalescent, okay? So does the species dynamics infer or have an importance in the genealogies? We can think of this about species, but I thought the other day that you can also think of this about geographical parameters, okay? Maybe you can say at some time there was a volcano exploding, so that a species was divided in 2 parts, or in a lake you have something that makes that your species, they get divided, and then they have to evolve on their own, okay? So this could be a way to decide if we use a double-level, multi-level model, or just a simple level model. Okay. Are there any questions? No, we thought not, and you will see that it will be. So at the end, the W we will manage to describe it better, to characterize it, and the way we manage to do it is with a recursive distributional equation. So I get to this, and I will try to get the intuitions actually. Okay, just here I could say a word of. So that's good. The way we manage to prove it is with a distributional equation, but we thought about many ways to prove it. On many ways we did not manage to prove it. But 2 weeks ago, Lambert and Scherzer managed to prove what's going on actually in T of the order 1 over S. So our result will be with T bigger. We don't really manage to prove things at this precise time that of the phase transition, but they managed to do it. And the way they do it, just say a word, is thanks to solving a Smoluchowski equation with mass loss. So I will just say a word on this because we thought about it. They managed to. So what's the Smoluchowski equation? It's a really classical tool to study coalescence, Kingman coalescence, but also additive, multiplicative coalescence. So the idea is that you look at PT of X, which is let's say the number of blocks with mass X. So you think about your blocks. The blocks, of course, when they merge, well, they accumulate numbers, okay? So you think about it as a mass. And what is going on? Well, in the Kingman's case, you will choose a block of size X, a block of size Y on you. So when they merge, you get X plus Y, okay? So when you lose 1 of X, you lose 1 of Y, you add 1 of X plus Y. And you can write this like Markov style. And then in the Kingman's case, yeah, you get if you look at the generating function, moment generating function, you get a classical Smoluchowski equation appearing, okay? But the thing is that, so these are the number of, not blocks, let's say species. Okay? So if you look at it species-wise, so when they merge, okay, we know what's going on, but meanwhile, they lose mass because they have less and less and less lineages between two moments that they, okay? So this is why, in a continuous way, your X will go downward in a coalescent, like the Kingman's coalescent, okay? So this is where the mass loss comes from. There were many results in last century about this, but not the one which is appearing in this model, okay? So this is really new and quite motivating, actually. So if you want to have a look, it's in the archive for 2 weeks now. Okay, so let me get back to our job. And let's say a bit more about W. Salud. Okay. Sorry, let me check what I wrote. Okay. So to understand more about W, we have to check well what's going on when Okay, so let's look at one of the S of t species at time t. So I will use again this picture. No, maybe I will draw another one. So, okay, I am time t, so I have a species. But where does this species comes from? She comes from the merging of two more antique species, okay? So at some time, as it was Kingman, you had two species, and they merged to create one, okay? So, and then you can go and on and on and on until time 0, okay? Well, this time, I will say that it's t times something, u, and of course, so the time backwards from t to ut is just 1 minus u times t. Okay? So at this time ut, you had a merger of two species. And then these two species, they had their proper size, and it was summed to get the new size of the species we are interested in it. Okay? So at this time, two species merge, and they have size. Well, if they have the same size so we call u, we said that it would be w over t. So if they have the same size, they should have like w1 over t, the first one, and w2 over t, where w1 is independent of w2, and they have the same law as w. Okay? So that means that at time ut, my new species created, giving a new species of size w1 plus w2 over t. Okay? And then what happened? So at this time ut, we have a certain size, w1. You start with w1 plus w2 over t. But then the number of genes, they decrease as a Kingman coalescent. And we know that from ut to t, we don't have any more changes or brutal changes, okay? So we just decrease as a Kingman coalescent number of blocks with the equation that you have upside. Okay? So then, at time t, ni of t will be, so I just change, so it's 2 over, so what is it? You have to take the time that you need, okay? So the time here is 1 minus u t plus 2 over the initial population, okay? So plus 2 over, okay, sorry, there is an error. So of course, these two populations, it's not w1 over t, it's w1 over ut, because we look at them at time ut. Okay, so you have 2 ut over w1 plus w2. And I recall you that our idea is that ni of t is more or less w over t, okay? So let's make thousands of approximations. And then we get w over t, but this t I can remove it. So w will be in law equal to 2 over 1 minus u times 1 minus 2 the W1 plus W2. Okay, so if everything goes well, and yes it will, the limit law, the limit random variable that I will obtain in my asymptotic result will solve this recursive distributional equation, okay? So this one where W1 and W2 are just copies, independent copies of W. Okay, so to prove this, okay. So to prove this, of course, we have to make like tons of expectation on saying that barely, essentially at a small time, things are going exactly as we think about it, okay? And that but it works, but I did not say absolutely nothing about this U, so I still have to characterize it, okay? So let's give the final intuition to have something about U. And this intuition comes from the following fact. So if we don't look backwards in time but forward in time, what we observe is just a branching, okay? We have one species divided in two. And if this branching process were a Yule process, well, it's known that this U has the factor over t. So you are at a time, and you look at the fraction of time till the future, till the moment of the explosion, okay? You are running a Yule process from t to 0. So you make the good time transform, okay? And you look at the next time, the first time of splitting in the Yule process, and what's happening is that U is uniform. So if it were a Yule process, U would be uniform. But there is a result of Beresticki and Beresticki in their paper about Brownian excursions on Kingman coalescent 2009, I think, saying that a reverse Kingman, it was an observation they made just, so we have to prove it maybe better. In the reverse Kingman, so if you look at Kingman in a reverse time, you have that this is a time change Yule process actually. And the good news, well, what we can check is that this time change does not really affect the time. So it's more or less like not changing the time in small times. It does not affect so much. So we can approximate a reverse Kingman by a Yule process. It's possible when t is small enough. Okay? And then we will be able to approximate our U by a uniform. And this is what appears in the limit. Okay. So maybe I just write the theorem. So suppose that you have, I will put some J indices. So suppose that you have small times, but they are bigger than the 1 over S, where S is the number of species from which you start. And, well, there is another condition that I won't write because it did not appear in I did not find any intuition to this one. But this is, well, I can write it actually. Yeah, it's nothing. And 1 over square root of nj sj. So n is the number of genes inside the species. Then I will have that tj square n of tj is converging in probability as j goes to infinity to 2 expectation of w over c. Okay? And w here is the solution of this recursive distributional equation. Okay? So there are really nice things here because we are able to simulate it quite easily thanks to this recursive distributional equation. Imagine that Mariana has far more powerful methods than me to simulate it, but somehow we managed to do something. And then we have an idea, an approximation, a numerical approximation of this expectation of W, which is 2 times something I don't remember. Okay, great. Are there any questions?
What is SG?
So I just put some J. So you take a sequence. The idea is that you will make your number of species, initial number of species on genes going to infinity. So S is the initial number of species, N is the initial number of genes, and you make them go to infinity. You take a sequence SG, S1, S2, S3. Okay? So I just put everybody goes to infinity according to the same index. Is that right? Okay.
So I have a question, well, more a comment than a question. So this thing seems to me like being one of these branching structure between into branching, right? Some branching in branching.
Yes, could be.
So
Yeah, should be.
Some of these techniques can be applied. The old.
So.
Or you use something.
No, we did not. We just used this approximation with a Yule process, but you don't really use this branching in branching because you have a Yule process, and inside you have some deterministic things. You are in small time, so you replace your.
I understand.
Mm-hmm.
I mean, but perhaps this can be some procedure to go for more complicated coalescence.
Of course.
Right?
Of course. So maybe, yeah, one observation. So one exercise, paper. So what's going on if we put some more complex dynamics? Okay, so if we let the species merge in a lambda coalescent way, and if we let genes merging in a lambda coalescent way. And of course, this should be possible to get extended. So what you should try to use, I think Airam is working on this actually. So maybe not exercise. So what you should try is you replace this S of t by the Berestiki-Limich approximation that I have. It's Vt, this is a function that I found, and this is a solution of an integral equation. Okay, so this you can replace it. So that means that in this you can obtain the same intuitions to get the recursive equation, distributional equation that you are looking for. Okay, so you do the same, and then on this part you should try to get the approximations with a Yule process or a branching process if you want something more complicated. So I guess so, yeah. But I guess these are good computation because in the Kingman's case it's not funny at all. So you have to take more things. But yeah, it should work. Eh? And actually I did not say, but W there is a unique solution in this case because this is a contraction, actually, this mapping of the law. So we were lucky in this case, we managed to have a unique solution. So we managed to characterize well the W. More comments? Okay, so I have until 30. Okay.
We still have like 17 minutes.
Great. So I will help you to solve this open problem, making the first structure. So what I will talk about now is how to generalize this idea. Okay? So in the Kingman's case, it's really, I mean, this model is really easy to define. Things are going well. Actually, I did not talk about it, but as you put some exponential independent exponential clocks on everybody, you don't have at the same time that two species merge and two genes merge. Okay? So nothing is going simultaneously. So now the question is, could I define some more general nested coalescence? So and the answer is yes, and this is the paper that went out of Ayram, Amaury, plus I and Jean-Gilles Duchamp. So, oops, Duchamp, L, Jegousse. And this is what we call the simple nested exchangeable coalescent. So the question is, could we generalize the coalescent mechanism? And the way we did it was in the lambda coalescent way. So let me just talk about lambda coalescent in 2 minutes. So the lambda coalescent is just a coalescent when you, with simultaneous mergers, okay? Multiple mergers, sorry, not simultaneous actually, multiple. So you let many lineages merge at the same time. Okay, so let me just give you, there is a nice Poisson construction of the lambda coalescent which permits to understand quite well what's going on. So let's look at this model, okay? So, okay, you can look at it at a time, continuous time Markov chain with values in the partitions, but I won't really talk about it. So let's look at a coalescence event, so conditional on a coalescence event. So imagine that you know that two guys have merged. So you look at this time, okay? You start with some lineages, and you look at the moment where you know that something happened, okay? So you condition on this thing. Okay, so what's going on for the other lineages? They can participate to the party or not, okay? And the way they will participate to it will be, so lineages, the other lineages, choose to participate, and they choose to participate in an exchangeable way, okay? Because these coalescents are exchangeable coalescents. This means, what does mean exchangeable? This means that if I put some numbers on the lineages, you can permute them and there is no problem, the law stays the same, okay? So they will choose to participate or not, but they do it in an exchangeable way. So you have a definity theorem applying, okay? And the way they do it is just like tossing a coin, tossing a coin, and if they have 1, then they merge with these two guys, and if they have 0, they don't merge with those two guys, okay? So what is the rate? So imagine you have B blocks, or B lineages, okay? And each k-tuple of them will merge at rate, well, for k guys to merge, so you need that k minus 2 of those one have 1, and b minus k have 0. On this, you sum over all the values of x. On x, of course, you choose it according to a measure lambda, and this measure is the definitive measure over these two things, okay? So this is a finite measure, or probability measure if you want, actually, okay? But this I can write it in another way, of course. So I can multiply and divide by this minus 2, I can put it in a measure. So you have this integral of xk, 1 minus x b minus k times nu dx, okay, where nu dx is just lambda over x2. And what you will ask in this case, if lambda is finite, you will ask that the integral of x2 nu dx is finite, okay? So, I have 5 minutes to write a lot of things, so that I won't write a lot of things. But we can have the same picture in mind to build an exchangeable nested coalescent, okay? So, we are able to define and characterize general exchangeable nested coalescents on the same way, with the same picture. So let me just write it. Okay. So suppose there are B species, okay? So the thing is that it's more complicated, of course, with the notation, because we have to define how many species we have and how many genes we have inside each species, okay? So you have B species with G1, G2, GB genes inside each of them, okay? Great. And we want to just write the rate at which things are happening. So a given k-tuple of species will coalesce with inside I1 until IK genes also coalescing. And so the picture is the following, okay? You have some species, and at some point they merge to a big one, and the genes which were inside, they will merge at the same time, okay? Some of them will merge at the same time, okay? So this is just the number. So this is L1 among G1, L2 among G2, etc. And if there is a species that does not coalesce, well, of course, the genes cannot coalesce with the other. They are stuck in their species, okay? So with this picture, you can imagine quite easily that, so I will use P instead of X. So this is the same thing as the lambda coalescence. So you have P to the power k minus k. Okay, I will write it as the right-hand way. So p to the k, 1 minus p, b minus k. And then you have a product from j equals 1 to k of the integral of q to the ij 1 minus q to the gj minus ij. Okay, I will have this definite measure mu dx, and here you go. Okay, on everything, I integrate it, made a huge integral. So what I have to choose, I have to choose my p. So let's call it nu yet, dp, and I have to choose my definite measure too. So d mu. So it starts to be really sad because we have a measure on 0, 1 times the probability measure over 0, 1. Okay? Well, it's sad, but the picture is complete. Okay? And so, just to stop, we have to ask things over this nu, but a bit the same kind of things than here, than in the lambda coalescent case, than here. Okay? So we have to ask also that on species-wise, at the level of the species, you have the good hypothesis on the measure. So you have to ask that the integral of nu dp, how did I call it? Sorry. Yes. So the integral of nu dp d mu times p square has to be finite. So it's exactly the same as here. You ask that you see these two species rising, and this comes just from the same picture. And so this picture is just the conditionalization, if you want, of two species merging. But there can be other things because you have things going on at the same time. So you can have somehow one species, one big species. Imagine you have in this B species, you just have one that tossed the coin that got one. So it does not merge with anybody. It's alone, but it's somehow activated. And while it is activated, you will have two genes inside which are merging. So what does this mean, activated? This means that if I add some species, B plus 1, B plus 2, B plus 3, and they get one in the toss a coin, they will merge with my activated species, okay? And this, so you can write it with the integral of nu dp d mu. So how do I activate my species with a probability p? And how do I have two genes merging? You have the integral of q to q2 mu dx, mu dq, sorry, which has to be finite, okay? So this makes a difference actually with the classical lambda coalescent, because in the lambda coalescent, this is a measure, but here this is a probability or a finite measure, and you have to ask her to integrate q to have a second moment, okay? And well, and that's all. So that's what we did with Amaury.
So you cannot use beta and beta?
No, you cannot use beta and beta. What you can do, for example,
I'm surprised, because in this beta coalescent you have these nested trees of beta.
Yes, what you can use, for example, is beta in Kingman. But beta in beta, you have to check very well the powers the parameters that you use. So, for example, if you want a beta.
I can imagine you cannot do it for any parameters, but
yes, exactly.
What is that this beta has so nested? Stable trees, level trees.
Yeah, it's possible. For example, you take nu as nu prime dp dA dB times measure, so how did I write it? I got it. Times a Dirac on a measure AB, okay, the d mu, okay, and then this measure AB is a beta 1 with A and B positive, okay, and then you get, this way, you get an easy hypothesis to solve so that it's well defined. But it's not whatever beta that you want. Mm. Thank you. Any more questions? Okay. So now let's solve problems.